Hello everyone. In this lecture, we are going to discuss about K-means clustering in machine learning. K-means clustering is a popular unsupervised machine learning algorithm which is used for partitioning a dataset into a predefined number of groups or clusters. The goal of this method is to group similar data points together and discover underlying patterns or structures that are available within the data. The partitioning is to be done in such a way that interpoint distances are small compared to the distances to points outside the cluster. That means we have to minimize the distance between the points which is lying inside the cluster compared to the points which lies outside the cluster. This diagram illustrates the concept of clustering. So before clustering, we have these points all are merged together. We have blue points, red points and green points. After we apply clustering, we can see that all the similar data items are grouped to form a cluster. So here we have three clusters. All red points belongs to cluster 1, green points belongs to cluster 2 and blue points belongs to cluster 3. So this is the idea of clustering. Now let us see the formal definition of K-means clustering. Consider that we have n observations or data points which is denoted as x1 to xn, where each xn is a d-dimensional vector in a Euclidean space. The goal is to partition these n data points into k clusters. We assume that the k is given. Now, the objective is to find a set of cluster centers, also called as centroids, which is represented as mu1 to mu k, such that the data points assigned to each cluster are as close as possible to the cluster center, which thereby minimizes the total within cluster variance. Within cluster variance means we have to minimize the distance between the points which lies inside the cluster. The objective function for K-means clustering is defined as J is equal to double summation of Rnk into Xn minus mu k whole square. Here in the first summation, n indicates the total number of data points. In the second summation, k is the total number of clusters. Xn is the nth data point, which is a d-dimensional vector. Mu k is the centroid or center of the kth cluster. And Rnk is the binary indicator variable which takes either value as 0 or 1. So if any data point xn is assigned to a particular cluster k, then Rnk will be 1. If it is not assigned to that particular cluster k, it will be 0. So the goal here is to minimize the objective function. To minimize the objective function, we can use the EM algorithm that alternates between two steps, namely expectation step and maximization step. Here E represents the expectation step and M represents the maximization step. First, let us see about expectation step. Here we minimize the objective function J with respect to the cluster assignments R and K and keeping the cluster centroid mu k as fixed. That is, for each data point xn, we will find the closest cluster centroid mu k and set the value of Rnk as 1 for that particular cluster and 0 for the others. This assignment will minimize the square distance that exists between the data point xn and the cluster centroid mu k. This assignment can be formally expressed as Rnk is equal to 1 if k is equal to argmin of xn minus mu j whole square, 0 otherwise. That means if there is only minimum distance between the particular data point and the cluster centroid, then we can assign this particular data point to that particular cluster k, which is represented as 1. Otherwise, it won't be assigned to that cluster and it will become 0. So this step ensures that each data point is assigned to the cluster whose center is the closest, thereby minimizing its contribution to the objective function. Now let us see about the second step in EM algorithm, that is the maximization step or M step. Here we minimize the objective function J with respect to the cluster center mu k and keeping the cluster assignments R and K as fixed. Let us consider the objective function J of the K-means clustering and apply the partial derivative for this equation with respect to mu k, which can be expressed as shown here. Here, since only the terms involving the cluster centroid mu k is contributing to the derivative, we can remove the summation k is equal to 1 to k because it represents entire clusters. So this equation can be written as dou by dou mu k of summation of n equal to 1 to n Rn k into xn minus mu k whole square. By expanding this distance term, we can write it as xn minus mu k transpose into xn minus mu k. By multiplying these two terms, we can write it as xn transpose xn minus 2xn transpose into mu k plus mu k transpose into mu k. Now let us take the derivative for this equation with respect to mu k. We can write it as minus 2xn plus 2 mu k. Since we don't have mu k term here, this will go off. And here if we apply the derivative with respect to mu k, this mu k will become 1. So it is 2 minus 2xn, and mu k transpose mu k is nothing but mu k square. So if you apply derivative for mu k square, it will become 2 mu k. Now by taking the minus 2 outside, we can write it as minus 2 into xn minus mu k. So the derivative of the objective function j with respect to the cluster center mu k can be written as dou j by dou mu k is equal to minus 2 into summation of n equal to 1 to n Rn k into xn minus mu k. To find the minimum, we can set this derivative to 0 as mentioned here. Further, we can simplify this equation by dividing both sides by minus 2. So this can be written as summation of n equal to 1 to n Rn k into xn minus mu k is equal to 0. Further, we can multiply these terms and we can express it as summation of n equal to 1 to n Rn k into xn. We can take this Rn k into mu k right side. So it becomes is equal to n equal to 1 to n Rn k into mu k. Since mu k is constant for all the terms in this sum, we can take this mu k before the summation. So let us write this term in the left side. So mu k into summation of n equal to 1 to n Rn k is equal to summation of n equal to 1 to n Rn k into xn. Now let us solve for mu k. So this can be written as mu k is equal to summation of n equal to 1 to n Rn k into xn divided by, we can take this to denominator, that is n equal to 1 to n Rn k. So this is the equation for the new cluster centroid. So thus we update the cluster centroid in the maximization step. The numerator here is the sum of all data points xn that are currently assigned to the cluster k. Denominator is the count of the number of the data points assigned to the cluster k. And the equation minimizes the sum of squared distances from the points to the centroid, thereby reducing the objective function j. Now let us see about the working of EM algorithm for k-means clustering. In this figure, we have the plots from A to I. So in the plot A, the green points denotes the data set in a two-dimensional Euclidean space. The initial choices for cluster centers mu1 and mu2 are shown by the red and blue crosses as shown in this diagram. In the plot B, we perform the initial expectation step or E step. Here, each data point is assigned to either the red cluster or to the blue cluster according to which cluster center it is nearer. So if the data point is nearer to the cluster center red, then it is assigned to the red cluster. If it is nearer to the cluster center blue, it is assigned to the blue cluster. So after this E step, in plot C, we perform the maximization step. Here, the cluster center is recomputed to be the mean of the points assigned to the corresponding cluster. So after updating this cluster center, subsequently we perform the E step and M step alternatively from the plot D to I until the convergence. So in the ith step, we can see the convergence where all the blue points are more or less assigned to the blue cluster and red points assigned to the red cluster. This figure presents the plot of the cost function j given by our previous illustration, which is essentially a measure of total distance that exists between the data points and their respective cluster centers. This plot shows the cost function's value after each E step and M step. Here E step is represented using blue points and M step is represented using red points. This is expressed as the algorithm progresses. The green line connecting these points illustrates the rapid decrease in the cost function, which indicates that the algorithm is effectively clustering the data. And the plot also shows that after some few iterations, the cost function j levels off as shown here. It means that the algorithm has been converged. So thus we have seen about the k-means clustering and the working of EM algorithm in this lecture. Thank you.